Hi there, and welcome back to Chapter 3.3 from Stevens' Matrices, Vectors, and 3D Math. This is our second video from this chapter, right? And in this one we're going to talk about the projectile in motion in 3D. And the first video from this chapter talked about the projectile in motion in 2D, and I'll just go back to that for a second. And this is just the example from the first video. Projectile in 2D, right? And basically what we came up with was when we integrated the acceleration vector to get the velocity and then integrated the velocity to get the position, we wound up with this position function, which gives us the position in the xy plane where x is distance along the ground and y was height above the ground. And so this vector valued function, the first part was x of t, and the second part was y of t. And it had a lot to do with the initial velocity vector, which had an angle of elevation equal to theta, and then some length of that vector, which we called v naught. Right? So a lot of that stuff sitting in here. And then some initial, it might start at some initial height, v naught, theta, and there's the acceleration due to gravity. Alright, so basically the components of the three-dimensional model are essentially identical. We just now have a new dimension in the distance. Instead of having x determine the distance along the ground, we're going to give our ground 2 dimensions. So let's go to the 3D case here. And so this is what our projectile looks like in terms of the coordinate axes. We have x and y. This x and y plane now determines where in sort of a field, a two-dimensional field, the projectile can land. Right? And z will is now the height. So that equals the height. And it plays the role. Before in 2D, y was the height. Right? Now z is the height. But aside from that change, the actual function determining the height is identical. What gets switched up is that the x and y now both denote the ground position. Okay, and so the way these projectile functions, position functions are determined requires an initial velocity vector. And so this is what I mean by an initial velocity. So this is sort of a launch vector, right? And now instead of being just in 2D, it's in 3D. And before, when we did this in 2D, right, we had x, y, and this angle of elevation for the launch vector we called theta. That is actually now called phi, right? In 3D, this angle phi plays the role of theta in 2D. Right? So that's the angle of elevation of the turret, if you will. Right? And then it has some length, which gives you the initial speed, and then this x, y, z is telling you the direction in which it's heading. Right? And so it's pretty easy to spot through a little bit of triangle trig that this value of z through triangle trig on this triangle, z is just equal to the size of v, the length of this hypotenuse, times the, let's see, the sine, I almost wrote cosine, times the sine of phi. Right? And so the next thing I want to look at is this d. All right? I'm going to think of d as just as a distance. So d, as I'm talking about here, isn't necessarily a vector so much as the length of that line. Right? And so again, if you look at this triangle, d is just going to be the size of v again, only now it's going to be the cosine of phi. Right? And so that's going to allow me to get x and y pretty easily. Right? X right here, x is going to be d times the cosine of theta, but d, I already figured it out up here, is the size of v cos phi cos theta. Alright, so that gives you my x. And likewise, my y is going to be d times the sine of theta, but d, again, I already have, is the size of v cosine phi sine theta. Right? And so that's what gets me all this stuff here. X, Y, Z. So it's just basically that's just triangle trig. Right? And the setup for 3D looks just like in 2D, except Z is now the height instead of Y. The angle of elevation is called phi instead of theta. And the initial velocity, or the speed itself is denoted by v naught. That's a scalar. That's just a number. But that initial velocity vector has an x component, a y component, and a z component obtained from right up here, from triangle trig. Alright, and so when you put these into the three-dimensional form, what we have is this position vector, right? Or position vector valued function, where this is x of t, this is y of t, and then this is z of t. And it's worth pointing out that this z of t, if you look back on the 2D portion of this video, the height was right here. And if you look at that and compare it to this, the height function is identical, except we have a different name for that angle of elevation now. Right? And then the x component and the y component are no longer just, it basically breaks up this x component into the two different parts. The part that's going in the x direction and the part that's going in the y direction, as depicted in this graph. So if this is sort of the vector in the xy plane, I have an x part and a y part. The x part is d times the cosine. So the x part looks like this, and the y part looks like that. And if you notice, all you then do is throw a t to show that it's increasing in those directions in t. So it really is just a redo of the two-dimensional position functions. Only now that the distance on the xy plane is replacing what used to be the distance just along the x-axis. Okay, and by the way, the following, and all of this stuff for the projectile in 3D, all of these formulas are identical. It hits the ground at this thing that we call T star. I derived it in the last video, but it's basically taking this height function, setting it equal to 0. That's when it hits the ground. The total distance, you figure out when it hits the ground, right? You plug that into your x function over here, plug that into your y function over here, right? So that's what I mean by x of t star, y of t star. But again, remember we're down here at x, y. We want this distance. That's going to be x of t star on the x-axis, y of t star here. And so this is the hypotenuse. It's just the square root of x of t squared plus y of t squared. Right? You can find out when the projectile hits its maximum height by taking the derivative of the height function, right? This is the height function. Take that, differentiate it, set it equal to 0, and we call that t tilde. That's when the ball or the projectile hits the highest point. And then if you want to figure out what is the highest point, you just take t tilde and stick it back in to the height function. Right. You can also get the velocity on impact, where you just differentiate r. Right? If r is the position, I take the derivative and I stick in t star. The z component of that will give me the velocity in the z direction, and the x and y part will give me the velocities in the x and y direction. So basically all I have to do is take the derivative of r, plug in t star, that'll give me the velocity vector, and I take the length of that vector, and that will give me the speed on impact. And again, these formulas look almost exactly as they do for 2D. Alright, the only difference is that phi, I'll put that down, phi plays the role that theta did. Alright, and the total distance is determined by the distance in the xy plane and not just the distance on the x-axis. So basically I'm going to do the same example we did in the first video in 2D. In In this one, we had an initial height of 0, an angle of elevation of pi over 6, and an initial velocity of 80 feet per second. We use the English system for 32 feet per second on the acceleration. And whenever I do that exact same problem in 3D, I still have to come up with a, so if this is x, z, and this is y here, I still have an angle of elevation of 30 degrees. I call it phi now. But now I have to figure out where in the xy plane that's pointing. Right, so it's pointing somewhere in this direction, right? Oh, there's angle of elevation going up. And so in this position, for this particular example, we just say, all right, let's assume that the angle from the x-axis on the launch that is positioned 45 degrees from the positive x-axis, right? So you take your turret, you go out 45, and then up 30, and that's where you launch from, at 80 feet per second. All right, so now you can plug this in, and in fact, I'll wait on this. Let's wait right here. This is when the ball hits the ground, because I'd like to show you where that comes from. It's really not that complicated. But if I look at the position function that was on the previous page, and I just plug in V0 is 80, theta, that's the angle from the x-axis, is 45, which is pi over 4. Phi was 30, which is pi over 6. Do it again here, here, and here. H is the initial height, that was 0. 80, and again, pi over 6. All right, and then G is 32. When I plug all that in, right, and simplify, I get to here, and then simplify some more. I get this is my position function. But now it's only valid, right, and remember, this is x, y, z. It's only valid until it hits the ground. As soon as this projectile hits the ground, this thing is not valid. So I have to figure out when does it hit the ground. So you can start these problems by determining when it hits the ground using this formula. And that's pretty brutal, right? You got to really get everything right, and there's a lot of room for error. It's actually easier to get this 2.5 by looking at the height function. That height function is 40t minus 16t squared. Sorry, 16t squared. If I set that equal to 0, that's going to be when, if I solve for t, that's going to be when it hits the ground. That's going to give me t times 40 minus 16t equals 0. So that means it's going to hit the ground at t equals 0, or, well, t equals 0, I don't care, but that's where it started, right? Or where 40 minus 16t equals 0, and that's just t equals 40 over 16. And 40 over 16 is 2.5. All right, so I have the position for this projectile for all time, but it's only valid when t goes from 0 to 2.5. All right, so suppose I want to find where the ball lands. I just take my 2.5, I stick it into the x function, which is right here. Take the 2.5, stick it into the y function, which is right here. And that's going to give me where the ball is going to land. And it should make sense that both of these are the same, because when I launch this thing, if this is x and this is y going into the page, 45 degrees splits that right down the middle. So that's along the line y equals x. So they're going to be the same, and that should make sense. The total distance traveled in the xy plane, the total distance, where it lands down here, is this going to be this 122.5 squared, or 50 root 6 squared, whichever one you want to do, plus 50 root 6 squared, square root, so about 173. So the distance that it travels in the xy plane is about 173 feet. Right. The maximum height, getting the time of that maximum height is actually the way I would do it. In the book here, I use the formula. But it would actually be, it's just as easy to derive that formula. If you look at the height function, right, there's the height function, which is 40t minus 16t squared. That's, say, my height, right? If I take the derivative, that's 40 minus 32t. And that's h primed. If I set that equal to 0, 40 minus 32, t equals 0, I get t equals, what is that, 40 over 32, which is 1.25, or 5 over 4. And when you plug that into the height function, you'll get 25 feet. Or you can just use the formula from the previous page. Either one works. Neither one is particularly trivial, right? These things probably should be done with a calculator at least, and preferably software, because then you just code it all up. And let's see, the speed on impact. Well, I have to take the impact time, right? This 2.5, that's t star. That's when the ball hits the ground. I plug that into the velocity function, right? And where did I get that velocity function? Well, if you take a look at our position function, right up here, this is r, right? This is the position function, which I call r of t. If I take the derivative, term by term, I get 20 root 6. Derivative, 20 root 6. Derivative is going to be 40 minus 32t, right? And then I'm going to plug in t equals 2.5, so that's where the 2.5 comes in. And when you take all these numbers, square them, add them together, and then take the square root, you actually get 80. So the speed when it hits the ground is 80 feet per second. And it's worth noting, we did this in the last video over the first half of this chapter, and we got essentially the exact same content. We got 80 feet per second on collision. That was the speed. We got the total distance covered was the same. And that should make sense, because really, if I'm in this X, Y, Z world, 3D world, my projectile is still lying in a single plane, the plane that projectile is in. So it's going to go the same distance, going to land with the same speed, and it's going to go the same height. All of those critical features remain the same in 2D or 3D. The only difference is that now it lands in a position on the plane as opposed to a position on the x-axis. So it's worth playing around with this. You might want to go to Projectile 3D, and basically, we put off, and I would grab this and open it up and run it. It's sort of got a little animation going. You have to plug in all those initial conditions. All right. The angle of elevation, the angle from the x-axis. Let's see, the angle of elevation, the initial speed, the initial height, the acceleration due to gravity, and then I just change my degrees to radians, put some bounds on my graph, and I'll take 50 steps to plot this thing out. All right, basically I have an X, Y, and Z. I'm going to sketch this trajectory in one point at a time. I'm going to do 50 points along the way till it hits the ground. And it's nice to do this to find out when it hits the ground. Hits the ground at this. This is what we call T star, which I call T star. If you're doing this by hand, I wouldn't recommend doing T star first. But if you're doing it with a computer, it tends to get these type of operations correct on the first try. So that's when it ends. That's when it hits the ground. And so the time steps, I'll go from 0 when it starts to T star when it ends, and I'll do 50 time steps. And there's just my position function in terms of X, Y, and Z. And then all I'm going to do is plot X, Y, and Z with plot 3. Remember, that's how we do three-dimensional curves in terms of parametric functions. These are just vector value functions, are just parametric functions. So this plots the trajectory, and then what this animation loop does is it plots every one of the points. So it goes through there, and you can actually see this projectile flying through the air. A nice little program. I suggest you pull it up, maybe play with it, and, rotate this thing around, make sure it looks realistic to you. This next page is really nothing more than saying, when we got R of t, we integrated A, the acceleration, to get velocity. And we integrated velocity to get the position. All I'm saying here is if you start with the position and take the derivative, you get the velocity. If you take the velocity and take the derivative, you get the acceleration. And that this acceleration is the exact same one we started with way back at the beginning of this chapter. Right? So for example, if this is the position, right, that we just derived, we take its derivative, that t just goes away, that t just goes away. H becomes 0, that t goes away, and I get 2 over 2, so that's 1, so I just get gt. Right? That's the velocity. Now when I differentiate one more time, these are all constants, so that becomes a 0. These are all constant, that becomes a 0. Right? So 0, 0. This just has a coefficient out in front of t. That coefficient is negative g. Right? So if you start with the correct position function and differentiate, you get the correct acceleration function. If you start with the correct acceleration function and integrate, you work your way back up. That's sort of the big picture, right? Acceleration, velocity, position. They're all connected through differentiation and integration. All right? And so here's an example. You know, if you have a position function and you differentiate it, you get the associated velocity function. And so it's worth pointing out that I take this velocity function and I plot the vector, this vector, originating from various points on the position curve. Right? So the position is determined by r, that's this blue curve down here. And then I plot a few velocity vectors along the way and position them to start at locations on the curve. And what you can see is that indeed these velocity vectors do in fact appear to be tangent to the position. Right? So it is true that it is sort of our recollection from one-dimensional calculus where you do get a tangent. Right? These arrows, these velocity vectors, are tangent to the curve being traced out by the projectile. And finally, I want to do one more little response whenever I have a projectile in 3D. I'm going to bounce it off the ground. It's actually really quite easy to do. What I'm going to do is if I have some incoming velocity, I'll call it v0, and suppose it hits down here, and you sort of have to figure out where that is, and you know where it is because you know when it hits, and then you plug that into x and y, and you'll know where it hits. And then what you want to know is what is the velocity right when it hits. And so when you get a bounce vector, it'll come off with the right magnitude. Right? And the way you do that is you just project across this normal. And what you wind up with is that the bounce vector, and we did this you should be familiar from chapter 2.6 on planes, I believe, is where we derived this particular bounce vector. And it's really quite simple. This is going to be the negative projection of v0 onto n, because the projection of v0 onto n is going to go the opposite way, right? And so the negative is going to go up like this, and that makes this particular vector here v0, right, minus that. All right, so you go down, minus that, or plus the negative gets you there, and then you want to do that one more time, right? And so you get v0 minus 2 of those projections, right? So if you go there, there, then you have that. That's the bounce vector right there, right? And this is something you'd write right into your code, right? You just give me, if you know the velocity coming in right here, and you get a normal. Well, if this is the ground, the normal vector to the ground is just parallel to the z-axis. All right, so it's 0, 0, and you can actually have any value there. You can have 15, you can have negative 2. It doesn't matter as long as the normal is going straight up or straight down. Okay, so that's how you get a bounce. If by chance your projectile loses some energy on the bounce, then all you do is make sure this thing loses some of the length from this thing, right? Because right now they will have the same length. So if you just put a damping coefficient out in front of there, maybe something like 0.9, then the bounce won't go as high as the incoming velocity. Like it won't go as high as it, like if you have a bouncing ball, it won't go up as high as it did every time. It loses a little energy on the bounce. So you just take it, throw a damping coefficient out there, make it less than 1, and you'll get some damping on your bounce. Right. If you make it 1, then these things, it'll just keep bouncing like that. And this whole bouncing ball thing is what we'll cover in the next chapter after we do Euler's method, which is a great way for advancing these Newtonian physics position and velocity vector valued functions. So we'll do that in chapter 3.4, where we will move around in 2 space and 3 space following these position vector valued functions like this. Right? It's fun stuff. We're really getting to the good stuff. So I will see you on chapter 3.4. I believe that wraps us up for this particular chapter, though. Bye now.